If you assume building an AI means simply letting a computer read the internet, you miss the reality. It is a digital landfill. It is packed with toxic content, completely unreadable gibberish, and bizarre redundancies, like a single random Amazon product description that has been copy-pasted 61,000 times across different domains. Training an AI on this raw data wastes millions of dollars in compute power. Instead of learning patterns, the model ends up memorizing useless spans of text or regurgitating specific pieces of copyrighted data found in the noise. To prevent this, engineers must extract a pristine, unique dataset from the chaos before the training process ever begins. But you cannot run a standard duplicate check on the whole internet. If you try to compare one web page to every other document to find copies, you create a quadratic equation. Attempting this across billions of documents would require thousands of years of continuous computing. Because traditional computing would take lifetimes, engineers had to invent hyper-fast, probabilistic mathematical shortcuts to cheat the limits of time and make modern AI possible. The first layer of defense is simple counting. Using n-gram models, the system scans incoming text and counts the frequency of specific word sequences. If a sequence matches the statistical patterns of normal English, the system keeps it. If it is a random jumble of letters, it is discarded. But grammatical accuracy is only a baseline. A perfectly structured sentence can still be toxic, explicit, or low value. To identify high-quality content, the system needs deeper classification. Fast text compresses vocabulary into a smaller space, instantly sorting text as safe or toxic. Then importance resampling measures this data against a high-quality target dataset. It dynamically shifts the raw distribution curve to match the target, ensuring a balanced diet of information. By using probabilistic classification and resampling, engineers strip away the noise and isolate high-value signal at lightning speed. Even after quality filtering, the system must address the millions of exact copies that clutter the web. Documents like terms of service or software licenses appear everywhere, and they must be removed without storing the entire internet in active memory. The Bloom filter uses multiple hash functions to flip specific slots in a memory-efficient bit array from 0 to 1. When a duplicate document passes through, it hits those identical pre-flipped slots and gets deleted. To prevent accidental collisions, engineers expand the grid. The Bloom filter sacrifices absolute certainty for memory efficiency, allowing server farms to scrub petabytes of data without crashing. A more complex challenge arises when documents aren't exact mirrors. If a user copies a web page but deletes a single comma, the mathematical output changes, and standard Bloom filters fail to see the overlap. To find these near duplicates, you would normally measure the Jacquard similarity between every document, but doing that across the whole web would reintroduce the impossible quadratic time problem. Engineers bypass this with min-hash. By randomly shuffling data, hash collision probability equals document similarity. To increase proof, hashes are grouped into bands. This creates a sharp sigmoid curve, allowing systems to instantly reject a 70% match, but delete 99% identical documents. This collision logic allows data scientists to surgically remove slightly altered text in linear time, entirely bypassing the cursive scale. The performance of modern language models depends as much on the efficiency of this data pipeline as it does on the complexity of their neural networks. By aggressively filtering and deduplicating the web, the system starves the AI of redundant noise. This strict process forces the model to learn true abstract concepts from high-value information rather than blindly memorizing digital garbage. To learn how to build these exact data processing pipelines yourself, head over to the Learn by Doing with Steven YouTube channel for hands-on tutorials. Mastering big data means having the right math to find the truth within the noise. To explore the big questions surrounding big data, tune into the Steven Data Talk podcast on YouTube Music, Spotify, and everywhere else.